Welcome back to Vibrations. This is week 2 and video 1. I'm going to deal with energy methods, virtual mass, and equivalent springs. Actually, probably should be written in the other direction because we're going to do equivalent springs first. And here we go. Let's make some purple here. So let's say that we have a situation where we have two springs in parallel. And we want to find out what the equivalent single spring is going to be. The big idea here is that these two springs, because they're connected right here, are going to share the same displacement. And each of them is going to have a force that's going to be whatever their spring constant is, either K1 or K2 in this case is labeled, is going to be multiplied by that same displacement. So the equation to use is going to be K equivalent is equal to K1 plus K2. So I'll box that and we'll come back in a second and maybe do a quick little derivation or just a proof maybe. We'll show how that's true. Now, instead of being parallel, we might have in a series, right? Two springs in series. Now, each of them is going to have a different amount of deflection, del 1 and del 2. But if you were to do a free body diagram on either spring, if you had a force here, the force has to be equal there, and then another free body diagram of the lower spring, you would say what they have in common is that P is going to be the same force internally everywhere for each of these springs. So the springs in series share the same force. And so the equivalent stiffness is going to be written as, and we could write this a couple of ways. I'm going to write this a little bit more universal before doing any algebra here. So there's K1 plus 1 over K2. Okay, so the thing to look for here is like, what are these similar to? I'm going to jump to that. What are these similar to? And you might erroneously say, oh, just like electrical resistors. They're actually the opposite of electrical resistors. Resistors in series add together. Resistors in parallel add in a sense of 1 over the addition of the reciprocals of all of them. I think I'm using that word correctly. And so they actually act very similar to capacitors. All right, so because capacitors act that way. And so, well, why does this work? Okay, so that's a better question. I should have left some more room in there. I could do a quick and dirty proof of this. And so, like, if you're going to take a look at the free body diagram right here, you would say, let me see if I'm going to say this the right way. Let me put it this way. If we had the total force, all right, so I decided to write it this way. The total force is going to be force 1 of the spring plus force 2 of the spring. Essentially what we've seen in the free body diagram, but this is true right here. So you would say, okay, well, that's going to be the del of the equivalent spring is going to be equal to the del times the 1 plus the del times the 2, and then switching colors here, we're going to see, well, all those del's cancel out, and we've just made a little proof right there. Yes, that's true. When they're in parallel, they add together. Let's go over here. There's a little bit more effort involved here. If there's two pieces of information, all of the forces are equal to each other here in the series situation, but the total deflection is equal to the deflection of 1 plus the deflection of 2, right? And so the deflection of 1 of the total is going to be the force over the equivalent is going to be equal to force divided, let me say the stiffness, I'm sorry, and then there's stiffness 1, right? So I messed up my words. All right, so you can believe that this is true, right? We could substitute in for the del and have the force divided by the stiffness. And of course, all of these forces cancel out. So we're left with that a 1 over the equivalent stiffness is equal to 1 over K1 plus 1 over K2, and of course that's the same thing that we set up here. Notably, you know, a lot of times people will write this for when there's only 2 springs. They'll say K equivalent is equal to, and you go K1 times K2 over K1 plus K2. And that's just doing a little bit of algebra and changing what we had up here into this. But if you had 3 3 springs instead in series, this wouldn't do you any good. But this would still be true. We could just keep adding more and more in the denominator here. So 1 over K1 plus 1 over K2 plus 1 over K3 and so forth. So that's why I'm just going to leave it in that respect. So we can also apply these same kind of ideas to beams, right, and to some other forms, like other types of stiffnesses. So for a cantilever beam, and this is, I've got this figure out of Shigley right here. Here's the maximum amount of deflection that happens if a force is placed on the tip. Now, because the force and the displacement are in the same place, remember that we could have the stiffness is really just force over displacement. And I'm going to go del, and we'll just say that that is equal to del. It's negative because they've decided that up is positive, and therefore it's deflected down. So you can see that the K that we actually get right here is going to be K is equal to F over FL cubed over 3EI. So instead you get a stiffness that's going to be 3EI over L cubed. The same thing can be true in the simply supported beam here with a load, a center load. Here's the maximum, so that's the del right there. So without going too much further, you can just see that we're going to end up with 48 EI over L cubed. Later in this session, but not in this video, in a later video, I'll show you that we're going to revisit this and look at the distribution of displacement as we try to see, get like an equivalent mass because of the mass distribution. I'm going to keep going on here a little bit longer. Another type of stiffness we might have is a rotational stiffness. You might remember the displacement equation because it just rolls off the tongue, TL over JG, or I guess it's GJ in this one. I like JG better than GJ. But that's going to be the angular displacement. So another type of stiffness that we could have is going to be the load divided by the displacement. So this is going to be an interesting one. It's going to be torque over angle, which is going to have units of Newton meters per radian. Or I guess you could have inch pounds per radian, foot pounds per radian, what have you, for the torque or the moment being placed on the thing. We also will have some amount of stiffness in terms of the torsional resistance right here. And so that's going to be this part over there. So we can write out the stiffness with the TL over JG as being GJ over L. And we also know that we usually have some type of circular cross section. So we could further substitute that J. We have to be a little careful here. I'll mention this in a second. We have to be careful with J's, right? So sad face, frowny face. J's get confusing because sometimes they're going to say a J is the area moment of inertia, and sometimes they're going to say J is the mass moment of inertia, and we need to keep those straight. So just remember, this J is going to be this J with the pi 4 d to the fourth over 32 is about the resistance of applied load, right? It's related to the area, the cross-sectional area of the piece, whereas some J's are going to be maybe related to the resistance to acceleration, and that's going to be the mass moment of inertia. So this is the polar area moment of inertia, and sometimes we'll call it the polar second moment of area, right? But that's the area moment of inertia as opposed to the mass moment of inertia of like a disk. Like so, often we used I in dynamics, right? But they use J sometimes here, and they'll go like for a disk, it's 1/2 mr squared, right? And this as units is like kilogram meter squared, whereas this one might have like meter fourthed is the area moment up right there. So just be on the lookout for that. But we can replace that here for the K, and this is the stiffness here. So we're going to go pi d4 G over 32L. Remembering that that is only for a circular cross section, but that's not that big of a deal because we almost always deal with circular cross sections. I think this next part is only for information only, that a real spring, if you know the wire diameter, which is the small d, is the wire, the diameter of the wire, and the big D is the mean, so you can see where this is labeled here. It's from the center to the center of the wire, so that's what that big D, a big overall, I don't want to say outside diameter because that's a little bigger, overall diameter, right? And you will see that little approximately symbol right in there too, right? So that's actually an approximation. But this right here will give you what the stiffness is, and the N is the number of effective coils. We don't have to go too much into that. Just realize that some of the coils get cut short, so you only want to count the full coils that are being involved. And I think that's enough for this one. I lost my thing right here. Yeah, 12 minutes long. Okay, so we'll make another video starting up from here, although there was a little bit left in here. So let me just one little thing like here. Okay, so here's a table out of another book. There's a table in your book, I believe. I should look up the table number or the Thompson book. I have it sitting right over here somewhere. I also have it sitting down below, where we could see here's a bunch of other types of stiffnesses that you might want to consider. So let me see if I can find, where'd you go? Here you are. And how come he's not doing it? Come, why am I having so many problems? Really? Seriously? Oh, there you go. You were just there, dude. What is wrong with you? Alright, I'm gonna get this. Yeah, these are great videos. Alright, I flip my thing back up in there. There you go. Alright, so there's Shigley. I was gonna open up and show you that, but you don't really care. Oh, and I guess I don't have the book open, so let me go to my vibration books. Open up the textbook. And let's see, close you down, make it enable scrolling, go to height, and go and down. I think it'll be at the end of this chapter. I think so. There you go. All right, and actually they didn't even have a stiffness. They had the beginning right here. So there's a bunch of different stiffnesses. Take a look at those. I think that's all I really had to say about that. All right, so that was worth it, all right? Sure it was. Almost 15 minutes.